for your kind invitation to give this presentation here. It's been a pleasure to follow this workshop. I don't consider myself neither an expert in control nor in reinforcement learning. So actually today I'm going to present some works whereby I started getting a taste for doing research in reinforcement learning, collaborating with experts, Roxana Radulescu from the University of Utrecht, and Manazar from the University of Amsterdam, and Nikki Orzan, who's been a PhD student with me at the University of Groningen. She graduated last week. So in fact, today I take the chance to present her work, the work we did together. For her PhD studies, and now she is starting a position at the University of Brussels with Annové. So let me give you a little bit of context for this work. It's a work in, so I do research in multi-agent systems. So that's where I consider myself, mostly active. It's in that community. So I'll give you some context first to position the work we've done here. So this is a paper I like to cite. It's from actually the Science magazine in 2015. So that was before AlphaGo, before LLMs, etc. They had a very nice issue with several articles, overview articles dedicated to AI research back then. One of them was this one on economic reasoning and artificial intelligence. I selected some quotes here that are particularly interesting from my point of view, because they position exactly the importance of economic theory for AI research. So economics is drawn to rational decision models because they directly connect choices and values in a mathematically precise manner. Critics argue that the field studies a mythical species, Homo economicus. So that's what the economists are interested in human beings, and produces theories with limited applicability to how real humans behave. Defenders acknowledge that rationality is an idealization, but counter that the abstraction supports powerful analysis, which is often quite predictive of people's behavior. So that's, well, the critique that is normally done in economics about economic theory, like, game theory, for instance. Now they go to AI. Artificial intelligence research is likewise drawn to rationality concepts, such as the one developed in game theory, because they provide an ideal for the computational artifacts it seeks to create. Core to the modern conception of AI is the idea of designing agents, so entities that perceive the world and act in it. The quality of an AI design is judged by how well the agent's actions advance specific goals conditioned on the perceptions observed. That's the, well, what we have been discussed throughout the workshop, right? This coherence among perceptions, actions, and goals is the essence of rationality. If we represent goals in terms of preference over outcomes and conceive perception and action within the framework of decision-making under uncertainty, then the AI agent situation aligns squarely with the standard economic paradigm of rational choice. So here they're saying, well, economists, especially empirical economists, behavioral economists, would criticize economic theory because it's too abstract. But it's for the AI designer that makes special sense, because in a sense it gives us a normative ideal towards which to struggle for the design of computational agents. And then they go on, they say, thus the AI designer's task is to build rational agents, or agents that best approximate rationality given the limits of their computational resources. In other words, AI strives to construct out of silicon or whatever an information as synthetic Homo economicus, perhaps more accurately termed machina economica. Actually, here I correct the Latin of the authors because they wrote machina economicus, which of course is not correct. So it's machina economica. Well, I find this particularly inspiring because it tells us how economic theory, in particular game theory, which is what I'm going to use in my talk, can be informative for the design of computational agents. Now I go a little bit fast forward. This is a paper from 2 years back, Open Problems in Cooperative AI. Since machines powered by artificial intelligence are playing an ever greater role in our lives, it will be important to equip them with the capabilities necessary to cooperate and to foster cooperation. Now, this is very interesting because cooperation has been a big puzzle for economists, especially in the paradigm of rational choice. So why are we cooperating in situations where actually it makes it beneficial not to cooperate from an individual point of view. So that's has been one of the big dilemmas and puzzles, and there have been libraries written in economics about the paradox of cooperation and how cooperation emerges in a rational choice context. And this is not the first time. Of course, this has been well, a popular paper, and it's used, of course, to motivate a lot of research, and it's an interesting one which I recommend. But I have to say, this idea has been around for a while. So here I have a paper that actually Fernando Santos told me about last week from 1986, Cooperation Without Communication. So AAAI 1986. Intelligent agents will inevitably need to interact flexibly with other entities. The existence of conflicting goals will need to be handled by these automated agents, just as it is routinely handled by humans. Again, here, cooperation as a way of resolving conflict of interest. So this was, of course, in the age of symbolic AI. So this was written by the people working in the logic group. Interestingly enough, this paper, the second one, doesn't cite this one. But it's to say, like, so the context of what I'm going to tell you is really this idea that we can use economic theory, especially game theory, to sort of design rational agents, computational agents. And the problem I'm going to focus on is the problem of cooperation. By the way, you can, of course, interrupt me at any time during my talk. So where are we going to study cooperation? Are so-called public good games, public goods problems. So what is a public good? Example, a lighthouse. So a public good is something that once it's realized, it can be benefited by anyone without sort of gates or without fees. So once a lighthouse has been constructed, every seafarer will be able to use it. Not only the ones that spent to realize it. These are typical, the typical situations in which free riding might exist. The public good can benefit everyone, so why should I contribute financially or effort-wise to realize the good? We see that with students, right? If they have to work on a project together, the common good, the public good would be everybody puts a lot of effort, they get high grade, everybody is somehow happy. But obviously, if the rest of the group does a lot of effort and I do less, I'm sort of better off because I don't spend any effort. So that's the public, those are public good problems, and we are going to sort of toy model them to a large extent. We're going to look at the interactions where players own some seed tokens, and they can decide whether to invest them or not in the realization of a public good. So they have some money, and they can decide to cooperate, so invest in the public good, or defect. So don't invest hoping that the rest realizes the public good. Then we will use a certain parameter, f, which is a multiplier factor, so-called. That is essentially the amount to which the investments will be multiplied once the good is realized. And the idea is that, well, this f, if we invest, the investment is multiplied by f, and then it's divided equally across all agents. So everybody profits equally from the realization of the good. So in a sense, this parameter is a very simple parameter of the game that modulates incentives, essentially. So if this is too low, below 1, then obviously nobody will want to invest anything because the return is too low. So if this is larger than n, larger than the group of agents, it's always rational to invest because I will have a return that offsets my expenses. And well, the issue happens in the middle. Oops. So let's see. Right. So if this parameter is between 1 and n, we are in the dilemma situation. We are in the situation in which it's better for me rationally not to invest, hoping that the rest does. And those are the situations typically, in a two-player situation, that would be a prisoner's dilemma. So we have a Nash equilibria that are Pareto dominated. So there is there is a social welfare, so there is a state that maximizes the social welfare, but that's not the equilibrium. The equilibrium is actually the worst from that point of view. Yeah. Right, but you have your coins in the pocket. You still have that. Right, so the point is, I prefer to keep your pocket money rather than put it in there. And if you put it there, but the return is too low, you essentially lose money. Yeah, good question. So, well, I would be better off if they invest, because the public good is then to some extent realized, and I will still get some money out of that investment that the others do. So I will keep my pocket money and get a fraction of the public good. If, of course, if everybody is rational, say like in the prisoner's dilemma, nobody contributes to the public good, so we just keep our pocket money. Yes, yes, yes. So that's the idea of the public good. I can profit from it even if I didn't invest, because I cannot create fences for, I cannot shade the lighthouse if I didn't pay for it. All right. So this is a simple situation. You can, you can model it more formally as a so-called multiplier factor game. So you have a set of agents. Everybody has an endowment. In our experiments here, we'll keep the endowments fixed and equal for everyone. There are two actions, cooperate or defect. And then this multiplier factor, this F, can be picked from a given set. And then we have the payoffs. And here so I should say, yeah, importantly, there are only two actions. So I cannot decide to invest only part of my money. Either I'm all in or I'm all out. So that's a simplification, of course, that makes the model sort of crisper, but one could study richer forms of interactions here. And then what are the rewards or the payoffs? This will be essentially consisting of two parts. So you can think of the green part here, the left addendum, is what I get from the realization of the public good. So you look at how much it has been invested, and you divide it by all agents. That's what you get from the public good. And then the right-hand side, or the right addendum, the red one, is what you keep by not investing. Right. So if you don't invest, you keep all your money. Otherwise, you put it all in. So I have a little bit of problems with the clicker. So the parameter, of course, that we are going to manipulate is this F. So because that will give us a way of modulating incentives here. And this brings us to the environment we're going to study, which you call extended public goods game. So the idea is that you can think of having a set of these F's multiplier factors. Those define different games. So here, for instance, in the middle, we have essentially a prisoner dilemma. So F is set to 1.5. We have two players. So, well, the equilibrium, even the dominant strategy is to play defect. So in equilibrium, this where you will end it up. But of course, the ideal situation is so social welfare maximizing outcome is cooperate. So it's a typical dilemma case. While to the left, we have a situation in which it is dominant to defect. And so where not only it's dominant, but also you get higher welfare. So it's a situation where you should not invest, essentially. And not investing is also optimal from a social welfare point of view. And vice versa, here it is optimal to cooperate also from a social welfare point of view. And we also have equilibria that realize that situation. So now you can think of, well, we have a spectrum of games of this type. And the interaction in this public good, extended public good games works as follows. You can think of sampling this value. Now this value is then observed by the two players with some uncertainty, so with the Gaussian noise model. So there is some error of the perception of the incentive structure of the game, essentially. And then these two players pick their choice, and we observe the results. So, for instance, here, the X agent, row agent plays C, so corporate, the Y agent plays D. So we get a payoff of 3 for row and 7 for column. So what we're going to, so what is in addition? So they have noise information about F. We also consider the possibility that these agents not only observe this value, but also carry out some form of inference in terms of maximum likelihood estimation using a Gaussian mixture model. So they have a little model of the uncertainty present in the interaction. This whole thing, essentially, it's a way of representing interaction where you have some level of uncertainty about the multiplier factor. So you have some level of uncertainty about the game you're playing in. And crucially, we want this uncertainty to capture also the situations that are, say, economically interesting, where you have these dilemmas. Yeah. That's not possible there. So what do you mean? Right. So not you cannot obtain it from this yeah. So these multiplier factors games are not fully expressive for all the two matrix games. Yeah, it's an important point. So basically, but what they allow you to do is, and it's just to capture the situation in which it's rational and also welfare optimizing to cooperate, rational and welfare optimized to defect, and dilemma situation in the middle. That's what we want to be able to model and to study learning in. Okay. Sorry, this is a little bit, there's some delay in the, because of course I didn't write it down, but in that way, but you can think of this as a partially observable stochastic game. So you could set it up in that way. So let's have a look at some baseline results in this simple model. Where we have two independent learners that learn through the reinforced algorithms, and we are looking at one-shot interaction, so one-shot games. And we have two settings. We have the setting where the agent don't use any model of uncertainty, and the ones where they use the Gaussian mixture model to carry out maximum likelihood estimation. So in these situations, so in this situation with no uncertainty, so where the perfect observation about F, well, everything behaves like you would like it, that you would expect to behave. So the learning converges to the dominant strategies or the equilibrium strategies, including in the dilemma situation. So here they learn to defect. So therefore, the public good is not realized. And here what I'm plotting is essentially the cooperation rate over the runs in the experiments. When we have uncertainty with standard deviation point set to 0.5, we see an offset, of course, happening. So you would expect the agent to have some level of, to be somewhat confused in some situations. So in the first setting, if in the games in which it is rational to defect, they learn it. In the other two situations where, so in the dilemma situation and in the situation in which it is rational to cooperate, we observe some error. So especially in the dilemma situation, there is a positive a non-null rate of cooperation. And in the situation in which they would all have to cooperate, and that would be the rational choice, they fail to converge to the optimal, to the rational solution. So we observe some, say in a sense, this level of injections of uncertainty disrupts a bit their ability to cooperate when it is rational to do so, but also increases cooperation in the dilemma situation. So in a sense, uncertainty in this environment leads to more cooperation in the mixed motive game, but that also costs the agents in the rightmost interactions where they should be choosing the cooperative strategy. Now, this is a sort of, this result sets a little bit the stage for the subsequent experiments I'm going to talk about, because now we want to probe a little bit this simple observation. And we're going to look at it in two ways. First, I'm going to we looked at what happens if besides this uncertainty, we enable agents to be able to exchange messages. So to basically learn to cheap talk. So to enable them to have some level of to support some level of emergent communication. And then we are going to look at this setting in which agents may have different perception of risk with respect to uncertainty. So let me go to the work on communication. So we want to probe a little bit that observation, and by studying communication as something that emerges, so there is no predefined protocol for communication, there is no predefined meaning for the signals that the agents exchange. So we basically are in the previous setting, but now we enable agents to, before choosing their actions, to exchange messages. So there is a fixed set of messages. In our experiments, it's 8. These messages are exchanged, concatenated, and then observed by the two agents. And then the policy would not only be dependent on the states, but also on the signals. And of course, they also, the agents will have to learn also policy, a signaling policy. So they will have to learn what to signal to the other player. So it's a simple communication layer added to the previous setup. Here you have a diagram, so diagrams in which we depict I'll give you a schematic of the experiments, of the setup of the experiments, where both players are uncertain, and to the left you have just they observe and then they signal. To the right you have the situation in which they also make use of uncertainty modeling in terms of maximum likelihood estimation. So what do we observe in this situation? So in the case, these are the plots that I gave you earlier. So we don't have communication. With communication, what we observe is the following. There is, in general, an increase in rate of cooperation, especially in the mixed motive setting, also in the dilemma situation. In particular, we see that uncertainty and communication leads to more cooperation, both in the dilemma setting, but also in the situations, the rightmost, in which it is rational to cooperate. In a sense, and this is in particular, this holds in particular for the situations, for the agents that can make use of uncertainty modeling. So there, the effect of communication and the model they use to carry out maximum likelihood estimation is particularly helpful. For instance, here in recovering more cooperation where it is rational to cooperate. And to obtain higher cooperation rates, pretty high cooperation rates, also in the situation in which it is not rational to cooperate, but it is to cooperate is welfare maximizing. So this is, in a sense, an interesting effect on the emergence of cooperation obtained through by just injecting uncertainty and some level of communication. Yeah. Yes. So this is it's very hard to interpret what they are communicating because it's something that so the signaling that takes place, it's not something we can easily interpret. But as I move, I will show you in the next experiments. So in this case, both agents are uncertain. Now we will see in the coming experiment that if we make only one agent uncertain, the other agent is certain, what we do observe is that the signals is used by the certain agent, the knowledgeable agent, as an effective way to exploit the ignorant agent. So there is, you can study what we cannot interpret, really interpret the message they exchange, but we can study them statistically and look, for instance, at correlation between the signal it is sent and the action it is chosen. So in an agent that will be exploited typically will correlate in a certain way their cooperative action to certain signals, while the exploiting agents typically will make as much as possible, will have as little correlation as possible between their choices and the signals they send. Yeah, so I think what happens here is that the signals may be used as an extra, effectively as an extra form of extra source of information. Now, here they are, so one way of, but this is actually a place where understanding theoretically what happens would be very helpful. So in this situation here, you can think they're both uncertain, and perhaps they are both trying to push the other agent to cooperate more. So they're both trying to exploit because that's what would give them more reward. And they both succeed to some extent. So it's a sort of, that's at least my interpretation of what might be happening here. So there is uncertainty and there's attempt at exploitation that succeeds to some extent. And that's why they're both pushed towards cooperation, even though it is irrational from economic theory point of view to do that. So they use perhaps you could interpret that as saying, I'm going to cooperate, do the same. And then they defect sometimes. So but sometimes they believe it, and that's why a cooperation gets higher here. That is my interpretation, but more research would be needed there to understand really what's happening and why. Yeah. So the best for a player there if they defect and the other cooperates, because that would maximize their reward. So it is plausible that that's what they're trying to do, and to some extent they must be succeeding because indeed you see the cooperation rate raises substantially. Yeah. Yeah. Sorry? Transformation of the estimate of case data that was getting message, at least from the architecture that was mine. Was it correct like that's the input, or because you said it's complex for you? So you mean the input for their action policy?
For the communication message, like from the
Oh, yeah.
that people say they have some kind of
No, the message is simply, so there is an alphabet of 8 symbols, and they have to choose which one to send. It's as simple as that. So it's totally so meaningless from. Yeah, yeah. It should not affect, right? So because it is really from a so economic point of view is what you would call a cheap talk. I can tell you anything, but there is nothing I can put on the table to make you believe me, right? So it is really so it is hard to interpret it, right, for us. But obviously, this extra layer of information that they're able to exchange, well, it is something that you know has an effect on the behavior. Yeah. Yeah, so we treated that as a hyperparameter. So it's a good question. So if I understand your question correctly, you could say, well, let's use just 2, right? It's a good point. Yeah. So that's also why I say, I mean, these are really just observational results out of experiments. I would really love to understand more what happens here, but also from the literature on the emergence of communication in reinforcement learning. There is little, from what I've seen, principled, say, theory on how to make those choices. But it's a good question, and I would not have an answer to, okay, what would happen if we just give an alphabet of 2 symbols? Yeah. Yeah. Probably would, yeah, the results would be less pronounced. Yeah. All right. Are there more questions on this? Then let me go on. So we also did the same sort of interaction, studied it also to get a better grip on communication here. When only one agent is uncertain, so there is now an agent that has full information about the game, and one that is uncertain, and still, and the fully informed agent exchanges information, so sends a message to the partially informed agent. And yeah, what we see here is that the partially informed agent, which essentially are these orange lines, the light one is the agent that uses a Gaussian mixture model. The other one is the one just takes the message as face value. So the perceived F as face value. So in both cases, so when there is no communication, the uncertain agent just is pretty confused, right? So there is no obvious movement towards the rational choices in none of the environments. But with in the presence of communication and in the presence of communication, in the absence of the maximum likelihood estimation model, we see that the uncertain agent is always robustly pushed towards cooperation. So and that's obviously, so our interpretation there is that it's that the messaging is used as an exploitation device, because that's where the informed agent can extract payoff from the uninformed agent, and that seems to be happening. if the so when there is no so that happens in this situation, it happens across all environments. When there is no model, we have a similar, so communication doesn't seem to have any real effect. So let me go a little bit further here. So I'll go a little bit quicker than on the last part. So here we studied what we refer to as risk attitude. So the idea is, okay, we have this observation that uncertainty seems to favor cooperation in the dilemma situations, with, of course, some qualification. We saw that the injection of communication can even strengthen that effect. Now, what happens when agents have different attitudes towards risk? Risk here is, when I invest, and I am uncertain about F, means I'm uncertain about the return of investment. So it makes sense to try to model, at least to some extent, how agents respond to this risk. And to do that, we use a multi-objective perspective. So the idea is essentially that we are now looking at the game by splitting rewards in two parts. So instead of having one reward, we have a vector of rewards. And we can think of this as being the reward that we get from the investment in the public good and the reward that we get from the money in our pocket. So that's how we basically abstract that. And we use, well, from the literature, multi-objective reinforcement learning. There are basically two approaches on how to then merge these vectorial rewards, either the scalarized expected reward or the expected scalarized reward. So those are the two options depending on where you put the expectation or the utility operator. We will be mostly using this. So let me go a little bit fast on this. Flashback, this is the multiplier factor game that I give you in one of the earlier slides. So what we're basically doing is treating collective return as one objective, individual return as another objective. We use colorized expected rewards to bundle them together. But what we also want to do is to add this attitude towards risk. And this attitude towards risk is modeled simply as this exponent beta, which can be made dependent on the agents. And this basically models the amount of utility we get from the collective investment. And here, of course, depending on the value of this beta, we can have risk aversion or risk propension. So if the function, the utility function is concave, we have risk aversion. If it is convex, we have risk propension. And intuitively, this is just standard modeling of risk in economics. You have risk aversion, where you prefer a sure thing from a lottery that may have even higher value. Vice versa, your risk propensity if you prefer the lottery, and your risk neutral if you're indifferent. And risk neutrality is what we have been using in the previous experiments. So we are sort of generalizing that. So now that we can model different beta, this also changes the perception of the game for the agents. And in this simple plot, I give you a way of recognizing where the dilemmas are, because now the dilemmas move around the spectrum depending on the beta. And we use the price of anarchy to model that. The price of anarchy is essentially a way in which we can measure the loss of social welfare that you obtain in equilibrium. So it's this ratio between the maximal welfare and the welfare in the worst Nash equilibrium. So in this plot, right, what we've been doing in the previous experiments, we're basically taking say, for the mixed motive or dilemma situation, we have an F of 1.5. So that's this purple line. And for beta equal 1, the price of anarchy would be 1.5. So that's how we interpret. You can interpret this diagram. So wherever you have this, we see that the lower the beta, and the lower the F, the more dilemma can occur. So what we are studying then, we're running experiments where now we have, say, a pool of 20 agents. We sample 4 of them to play the public good game. So now we have 4 agents instead of 2. We choose the Fs so that we have a good representation of all the possible interactions, from fully cooperative, fully competitive to mixed motives. And we study again the mean cooperation rate. And what we observe in this, so in this case, we have homogeneous preferences of risk. So every agent would have the same beta. Well, we observe that the higher the beta, of course, as you would expect, the higher the cooperation rate, because now basically our agents are more risk propense or risk prone, so we'll tend to cooperate more often, also in dilemma situations. And this seems to be, so we have the presence of uncertainty leads to more cooperation, especially so once we look at risk neutral, but especially risk seeking or propense agents. We also did experiments where now we take heterogeneous preferences towards risk, and the observation that we made in the previous case remain hold here, seem to hold here as well. So we have again that uncertainty leads to more cooperation for any attitude towards risk, but in particular, the more variety there is in terms of risk preferences. So where we have, so here we're sampling the betas out of normal distributions centered around 1. So the more variance we have, the more cooperation will occur. Okay, so let me wrap up. So what I described to you was a simple environment where agents are essentially somewhat uncertain about the game they're playing. And well, the focal point is, are of course dilemma situations that occur there. Uncertainty appears to play to have some form of impact, in particular positive impact towards the emergence of cooperations, with obviously also potential drawbacks. So potentially loss of rationally optimal choices in extreme cases, and also, well, we saw the possibility of deception in the case of information asymmetry. What I presented are all experimental results, observations, of course, that we also tested statistically, but we lack a theory of this. And it would be very interesting to embed this observation into, well, the computational theory of games. So this is something that we definitely would like to do. Thank you.